Assalamu alaikum. Welcome to lecture number 15 of digital signal processing. So students, in the previous lecture we have started our discussion regarding the frequency analysis techniques for signals. We get ourselves introduced with other frequency analysis techniques such as CTFS, which is continuous time Fourier series, along with CTFT, DTFS, DTFT, DFT, and finally FFT. In the previous lecture, we have started our discussion with the synthesis equation of continuous time Fourier series. So in this lecture we are resuming our discussion for continuous time Fourier series, and we will look at other techniques as well. So students, in this slide you can see that you have a square waveform which is comprises of multiple sinusoids, and you can see that it is a time domain view. And if you separate out all the components, then you will actually gain the frequency domain view which is shown in the slide, and this can be converted into that is time domain to frequency domain is converted with the help of Fourier tool. And by using Fourier tool we can actually convert our time domain signal into frequency domain, or we can say that we get to know the actual spectral components which are present in that complicated waveform. By looking at the expression written on the slide, which is basically the synthesis equation of any complicated signal, there are basically three coefficients which are A0, An and Bn, which can be used to analyze the strength of each individual component in any complicated waveform. And if we add up these individual component, then we will get the actual complicated waveform. That is, if A0, which is the DC component, An, which is the amplitude, pertains to the cosine waveforms, and Bn, which is the amplitude, pertains to sine waveform. So if we combine all these three components, or it is not necessary that all three components are present in any complicated waveform. So we may have only one component, or maybe two component, or maybe all three of them may be present in any complicated waveform. So just we have to add up all these components made up of cosine waves, made up of sine waves, plus the DC offset to get the original complicated waveform. So at this stage it is clear to you that waveform is comprises of multiple individual components, and with the help of analysis equations we can actually determine the strength, or we can actually comment on the presence of any component in that complicated waveform. That is, we came to the result that whether A0 is present in that complicated waveform or not, means DC offset is present or not. Next thing, the cosine waves are present in that waveform or not, and sine waves are present or not. So these components, which are obviously individual components, are present or not in any waveform, can be determined with the help of analysis equation of continuous time Fourier series, which is on the next slide. So here you can see that I have written the synthesis as well as analysis equation of continuous time Fourier series. So by looking at the analysis equation of continuous time Fourier series, there are three individual components that can be present in any complicated waveform, and the mathematical expression to determine these three individual components are written in the analysis equation part. First, A naught is given, then An, and then Bn, and their mathematical expression is written how we can determine the individual strength of each component. As we are interested in determining the individual components, so we are more likely dealing with the analysis equation. We have to put our focus on the analysis equation rather than the synthesis equation, because actually we want to explore the building block or the number of sinusoids or the nature of sinusoids or the number of spectral components and their quantities in any complicated waveform. So this we can achieve with the help of analysis equations rather than synthesis equation. Synthesis equation is used when we know these components and we have to add up these components to get the original waveform. But here it is not the case. Here we are basically interested in finding out the individual components or spectral components which are present in any complicated waveform. So we are more interested in the analysis equation. So if you have any complicated waveform and you have to determine whether it has some DC offset or not, you have to use the expression A naught, first expression highlighted by my pointer as this. This is the expression you can use to find the DC offset in any complicated waveform. And if you want to determine the cosine wave with a particular frequency, m is basically representing the integer number and it will be multiplied by 1 over t, which means frequency. So it is basically m into f, which means the particular frequency or integer multiple of that frequency. So if you want to determine the that component is present in your complicated waveform or not, so you have to you can determine with the help of this equation, which is am is equal to 2 over t integral ft cos 2 pi m t over t into dt. Similarly, you can find out the component Bn and its strength with the expression written in the last. But the interesting thing I want to add up here, these are the mathematical expression. Okay, fine. For synthesis equation, we actually assume some cases and derive the expression for synthesis equation. Likewise, analysis equations can be determined by using some assumptions or mathematical relationships. So I want you people to drive these relations mathematically by considering some waveforms, and you can actually present your work in the live session, and it is very interesting also. So I would like you people to do it before the upcoming live session. So your actual task is to determine the method or to figure out the method to figure out the individual components and their quantities in any complicated waveform, which is basically this equation. How you come up with these expressions, that y a naught is equal to 1 over t integral ft dt, why it is not something else, how we ended up with this result. I want you people to search out for this. Y in n we are multiplying it with the cos factor, y in bn with the we are multiplying with the sine. As we are discussing frequency analysis of signals, so we are basically dealing with the time domain representation and the frequency domain representation, as you all know, and we are discussing some techniques utilized to analyze the presence of any spectral component in any signal. So basically we are interested in some important relationships that has been developed to predict the nature of time domain or frequency domain representation. I mean to say that if I have some time domain representation, I can actually predict the nature of its frequency domain representation, or vice versa. If I have frequency domain representation, so I can predict the shape or nature for the time domain representation of that signal. So how we can determine this? We are going to learn in this slide. So basically you can see the relationship. We have continuous and aperiodic is written with the continuous, and in the second line we have discrete, and periodic is in combination with the discrete. So what is this relationship actually? In this relationship basically we are going to learn a transform pair, which means that basically we have two parameters of any time domain representation, whether our signal is continuous or whether our signal is discrete. Okay, fine. This is the one classification, and another classification is whether our signal is periodic or it is aperiodic. So we have to classify our signal whether it is in time domain representation or frequency domain representation, but for our easiness I'm considering that we are talking about the time domain. So if your time domain representation is continuous, then its spectrum must be aperiodic. Fine. But if your time domain representation is discrete, then your frequency domain representation will be periodic, which is written on the slide. Moving on to the next parameter, if your time domain representation is aperiodic, then the transform pair with aperiodic is continuous, which means that your frequency domain representation will be continuous. Similarly, if your time domain representation is periodic in nature, then your frequency domain representation will be discrete in nature. So by looking at these two parameters of time domain, that is continuity or discreteness, and the second one is periodicity and aperiodicity, we can actually comment the representation or nature of its frequency domain. Let's take example. In this example you can see that you have a rectangular pulse train, and you can observe that this rectangular pulse train is continuous in nature, which is written, as well as it is periodic, that is it is repeating its specific pattern after certain time, which is equal to Tp as marked in the waveform. You can see that you have a rectangular pulse train, and if you are starting from this point, then this exact shape is repeated after every Tp, and Tp is marked here. So you have a continuous waveform and periodic waveform. So now you have to predict the exact nature of its frequency domain. So by the knowledge of these two parameters, we are predicting that on the basis of continuity, yes, you have a continuous time signal, and continuous time signal must have a periodic spectrum. Fine. So we have write aperiodic here, Second thing is periodic. Your signal is periodic, and for periodic you already know that the spectrum must be discrete, so you have write discrete here. So by knowing these two parameters you are actually predicting these two parameters. Your waveform is continuous. Continuous means spectrum would be aperiodic, and your waveform is periodic, it means your spectrum will be discrete. So I'm going to display you its spectrum. We are not interested that how we get this spectrum, the actual values of this spectrum right now. We are not interested in that, but we are more interested in the pattern of this spectrum. And you can see from the frequency domain representation that it is aperiodic, which means that the pattern is not repeating after a certain time. At every instant you are getting different pattern, so it means you have a aperiodic representation in the frequency domain, plus your spectrum is discrete in nature, which you can see with the help of the dotted envelope. So dotted envelope is always used. I am highlighting the envelope. Dotted envelope is always used when you have to represent any discrete time plot, and if you use the solid line then it is showing the continuous time plot. So we are representing this with the help of discrete or dotted lines, so it must be a discrete time graph. And you can see also that you have a spectral lines which are at particular distance with each other. Not you have the spectral lines at all values, but you have the spectral lines at some specific values. So actually you have the discrete time frequency domain representation. And for your easiness, I have selected the plot of continuous time Fourier series basically, which is the technique applied on continuous as well as periodic signal, which is basically I have selected the signal is continuous and periodic. So by using CTFS technique we can actually ended up with this frequency domain representation. But before actually solving the mathematical equations, we can predict the nature of frequency domain representation by using this relation or transform pair. I have used another example which do not pertains to continuous time Fourier series example, but rather it is a graph which is continuous in nature and aperiodic as well. So you can easily comment that CTFT technique, which is continuous time Fourier transform technique, will be utilized to determine the shape of its frequency domain spectrum. But by using the above relationship which we have learned in this slide, we can actually predict the nature of its frequency domain representation. So actually you are having continuous signal and aperiodic as well. So the continuity in this signal is basically contributing to the aperiodicity of this spectrum. You can see that the spectrum is aperiodic in nature, and since the signal is aperiodic in nature and aperiodic is related to the continuity, so your spectrum will be continuous in nature. And you can see that your spectrum is continuous in nature, and you do not use the dotted lines here, rather you have used the solid line. So the continuous and aperiodic time domain representation will always result in aperiodic and continuous frequency domain representation. So you can try up with different combinations and come up with the actual idea or the actual representation of frequency domain. As we have discussed the analysis and synthesis equation of continuous time Fourier series, which are basically in the trigonometric form. Another convenient form is the exponential form of Fourier series or exponential form of continuous time Fourier series. And the analysis and synthesis equation for exponential form of continuous time Fourier series are written on the slide. Question arises in our mind that why we are using exponential form, why we are not restricting on the trigonometric form which we have learned in the previous slides. So students, both the equations are valid, both the forms are equally acceptable, but exponential form is basically more convenient to us in terms of calculation. You remember that in the trigonometric form we have three variables which we have to determine to actually analyze the signal, which are a0, an and bn. A0 is actually telling us the presence of DC offset, an is actually predicting the presence of cosine waves, and bn is actually predicting the presence of sine waves in any complicated waveform. But altogether we can only determine the exponential Fourier series coefficient, which is C of k. I have highlighted in this slide. This C of k is replaced by these the three coefficients, which are a0, an and bn. So we do not have to determine each of these coefficients separately. Rather, we have only one coefficient, which is ck, and we have to only determine the value of ck, and the equation is written on the slide. So if I want to determine the value of a0, a0 is equal to the c0. So if I determine the c0, I can say that I come up with the result of a0. And what about an and bn? An and bn actually combines together to form the cn. Means if I want to determine a1 and b1, it is the same as I come up with the result of c1. So actually the contribution of an and bn combines to yield the another coefficient, which is c1. So here we are not dealing with these coefficients a0, an, bn separately, but we are actually finding only one coefficient value, which is c of k. And by determining c of k, we actually come up with all the results of a0, an and bn. In analysis equation, you can notice one thing, that yes, you have continuous time Fourier series, which is also proving from the equation, as we are saying that it is Fourier series, which means your waveform is periodic. So for periodic waveform we are actually using the time period, because periodic waveform repeat itself after certain time. So we are using the t here, which is actually representing that the waveform is periodic in nature. Another thing, your waveform is continuous time, so we are using the integral sign, and integral is always used when we have to integrate the continuous time plot or continuous signal. And if we are dealing with the discrete values, then we use the summation sign rather than the integral sign. So in the analysis equation, these two things are representing that you are dealing with the continuous time Fourier series. Continuity is representing by this integral sign, and series is represented by this time period. And e raised to power minus j k omega t is actually the basis function. And interesting thing about basis function is that if the basis function is a negative in one domain or in one equation, then it must be positive in the other equation. All other thing remains the same. Another interesting thing we can notice in the synthesis equation, which is basically the time domain representation. As you can see that we are combining all the components to get the time domain representation, and it is basically the frequency domain representation. Analysis equation is basically an frequency domain representation, as we are finding the spectral components present in our complicated waveform. So by using the relationship we have learned in the previous slide, if our waveform is continuous and periodic, then its frequency domain representation will be discrete and aperiodic. So you can see here you are actually using the summation sign, which means that you have the discrete values and the limit is from minus infinity to infinity, not a single time period, but the limit is minus infinity to infinity. It means you can have several values, which means your spectrum is aperiodic. So you are actually combining the aperiodic samples to get the actual time domain signal. So you can see that continuous time Fourier series, you have used the integral sign which is showing the continuity, and for series you are actually representing this t. And if you are talking about the frequency domain representation, then its plot must be discrete, which is reflected by summation sign, and it must be aperiodic, which is represented by minus infinity to infinity, that any values can be present in that spectral component. Here I have included an example from which we can actually learn how we can use the continuous time Fourier series analysis equation to determine the spectral information present in that complicated waveform. So actually you have this rectangular pulse train, and amplitude is represented by A, time period is represented by TP, and the width of the pulse is actually denoted by minus tau by 2 to tau by 2. So it means the width of the pulse is actually tau. If you combine minus tau by 2 to tau by 2, then you will get actually tau. So I'm talking about this width. I'm highlighting with the pointer. This is the width of the pulse. So tau is the width of the pulse, A is the amplitude, and TP is the time period. Now first you have to look at the nature of the waveform, and you comment that this waveform is continuous and periodic. So we can use continuous time Fourier series analysis equation to determine its spectral component, and we are using actually the exponential form of that Fourier series. So we have to determine the Ck. So first C naught or Ck is equal to 1 over Tp integral minus Tp by 2 to Tp by 2. It means one time period, x of t and dt. This is the actual formula for calculating the coefficients values, and we have put the value A as the width of this pulse is A, and if we integrate this for 0 value, then we will get A tau by t. So the general expression of Ck is written here, and we have put k is equal to 0, so we get this expression, and at the end we get this result A tau by t. And for other values of k, we have to integrate this expression, and after integrating we are ended up with the result sine pi k f naught over tau over pi k f naught tau, and we know that sine theta over theta is sinc of theta. So we are getting up with the plot which is the same pattern as of sinc function. I have included the standard plot of sine theta over theta, or we can say the sinc function. Sinc function is basically this type of plot in which there is a central lobe or the main lobe as indicated by my pointer, and we have side lobes. The central lobe or main lobe is this one, and all other lobes are the side lobes. But as we are dealing with the continuous and periodic signal, we know that we will get the discrete and aperiodic spectrum. So we have plotted this function in generally by using the discrete time representation as well as aperiodic in nature, which is the nature of sinc function. It is not periodic, it is aperiodic. So students, by considering the previous example, we actually come with some interesting characteristics of time domain and frequency domain representation pertains to rectangular pulse train and the sinc function. So if we are considering that example, in time domain we have a rectangular pulse train which definitely has some pulse width, and that waveform must have some time period. But the characteristics we saw in the frequency domain are not the pulse train but the sinc function, which has the central lobe and the side lobes, or we can say the main lobes and the side lobes, and that lobes have some specific width. And another thing we saw in the previous examples, that we have the spectral spacing, which is actually the uh, consecutive distance between the two spectral lines. So there is some interesting relationship between these parameters of time domain and frequency domain. Lobe width is related to the pulse width, and how it is related with the pulse width? Lobe width is actually inversely proportional to the pulse width, which means if I am increasing the pulse width in time domain, the lobe width in frequency domain will be decreased, and vice versa. Next thing is spectral spacing, which is actually the difference between two consecutive spectral lines. So if time period is represented by Tp, then frequency is represented by f or f naught. So the relationship between that time period or frequency with the spectral spacing can be represented as time period is inversely proportional to the spectral spacing. If we are increasing the time period of our rectangular pulse train, then spectral spacing will be decreased, which means that the distance or the distance between two consecutive lines in the lobe is decreasing. The next thing is spectral density, and spectral density is actually the how dense our spectrum is, or the total number of spectral lines in the central lobe, you can say. And spectral density is inversely proportional to the spectral spacing, and by using the last relationship we have discussed, which is spectral spacing is inversely proportional to the time period, we can say that spectral density is directly proportional to the time period. So these are very interesting relationships, and with these relationships we can actually determine the other characteristics of time domain and frequency domain representation. We can verify the relationships we have discussed in the previous slide. In this plot, I have used the same rectangular pulse train and I have plotted its frequency domain representation with different values of tau, and tau is basically the pulse width. So you can see that in the first plot I have used the value of tau as 0.2 tp, which you can assume as the benchmark, and in the second plot I have reduced the value of tau to zero point 0.1, and in the last plot value of tau, which is the pulse width, is further reduced to 0.05. And we know that if we are decreasing the pulse width, we are actually increasing the lobe width, because lobe width is inversely proportional to the pulse width, which you can see from the graph. As the pulse width is decreasing, the lobe width is increasing. The central lobe is narrower and it is going to wide as we are increasing the pulse width. The next thing you can observe, we are not changing the time period of this waveform, so the spectral spacing and spectral density of these three plots remains the same, that there is no effect on the spectral spacing or spectral density of these frequency domain representation, as we are not changing the value of time period. Moving on to the next frequency analysis technique, which is continuous time Fourier transform. We are actually not interested in how we are getting these expressions, rather we actually want to analyze any real-time signal. So we are more interested in the equations of these techniques. But I have as already discussed that all these techniques have some limitations. So the limitation of continuous time Fourier series, which I have discussed previously, you can also comment that this can only be applied to the continuous time signal, not a discrete one. So yes, it can be one limitation. Second limitation, it can only be applied to the periodic signal, not aperiodic signal. But the particular limitation or more specific limitation is, you can say that you cannot analyze any real-time signal with the help of CTFS. Yes, it is a very good technique if you are going to solve it with the help of pencil and paper. So yes, it will give you the result. But if you are going to analyze any real world signal, so you are not assured that when it periodicity will be ended or whether it's periodic or not, because most of the real world signal are aperiodic in nature, so you cannot apply CTFS technique. Talking about CTFT technique, analysis equation is written on the slide, and as you know that it is a continuous time signal as well as aperiodic. So in the analysis equation we have used the integration sign, which is representing continuous time signal, and it is aperiodic, and aperiodic is represented by the limit of the integral sign, which is minus infinity to infinity. Rather than one time period, we are using the values minus infinity to infinity as the limit of integral function. And if you talk about the synthesis equation, you can say that yes, if the function is continuous in time and periodic in nature in the time domain, then it will be continuous in nature and as well as aperiodic in the frequency domain. So this can be represented by the integral sign and again the infinite limit used in the synthesis equation. So what's the limitation of this technique? It is continuous time Fourier series, and it cannot be applied to the discrete time signal, and it cannot be applied to the periodic signal. But more specifically, we can say that most of our real world signal are continuous as well as aperiodic in nature. So we can definitely and easily apply this technique. What's the problem with this technique? So the answer is, the problem is with the continuity of this function. As you have limited memory of your systems and limited speed processor, so you cannot store and process the continuous valued function. So you must convert that real world signal into the discrete value, and once it is converted into the discrete time signal, you cannot process it with the help of this technique. Yes, this technique can be useful if you have already have a signal, where a recorded one or the provided to you on the paper, and it will be continuous and aperiodic in shape. So yes, you can apply this technique, apply these equations, and you will get the result, and that results will be equally valid. But you cannot process any real world signal with the help of this continuous time Fourier transform. Another technique, which is discrete time Fourier series analysis equation, we use the summation sign, which is representing the discrete function, and as we are dealing with the series, which means periodic function, so we are representing the limit as n is equal to 0 to n minus 1, not the infinite limit, because we have some specific time period. And if we talk about the frequency domain representation, which is represented by the synthesis equation, so there we also get the discrete time plot and the aperiodic representation, which is represented by summation as well as the finite limit. Again, what is the limitation of discrete time Fourier series? We cannot process real world signal because real world signal are continuous and aperiodic. So we need any technique which can deal with that nature of signal, which is obviously the next one, DTFT. So here DTFT, discrete time summation sign in the analysis equation, and Fourier transform means aperiodic, and aperiodic is represented by the infinite limit. So you can see from the synthesis equation, you will get the plot which is continuous in nature and periodic as well, which is indicated by the integral sign and the finite limit. So here you can comment that with the help of this technique, which is discrete time Fourier transform, you can actually process your real world signal. Yes, no, there is some limitation of this technique as well. And what is that limitation? I will discuss it in the live session with you people. But I want you people to actually search out what's the limitation with this technique, which is discrete time Fourier transform. If your real world signal is continuous in nature, which is also aperiodic, so you can actually sample that signal to make it discrete in nature. And if once the signal is converted into discrete and aperiodic, you can apply this technique, which is discrete time Fourier transform. But actually we are not interested to apply this technique. We actually apply DFT or FFT, which are the later techniques. But what's the reason? So I want you people to actually explore this question, why we are not interested in utilizing this technique for processing real world signal. Rather we are interested in FFT or DFT. So I want you people to search or explore this question, and if you have any question or query related to this lecture, you can comment